All right, welcome everyone to this excellent video. This is where things start getting a little bit more beautiful, a little bit more complex, all right? There's beauty in complexity. There's also frustration in complexity and anger in complexity sometimes, so stick with me. We have a lot of extra videos, so this is the last thing for this week. But we're gonna do 2 examples in this video. It's gonna be a long video, and we're gonna do an extra example in an additional video if you would like more example problems to hopefully reflect more homework problems and more types of things that you can see. All right, so you guys are getting a bonus one over here, bonus video. So when we're trying to optimize, that's like finding maximums and minimums, maxima and minima, just like we did in the last video. So we'll look at local extrema and check the endpoints or the boundaries of the domain or the ends of the domain, however you want to phrase it. But sometimes we have situations where we have multiple variables, in which case we're going to have to substitute out one of the variables because we can't take the derivative. We can't find a relative minimum or maximum unless we only have one variable. Until next semester, when we'll do partial derivatives and Lagrange multipliers and higher dimensional functions. Really cool stuff next semester. All right, anyway, so we got 2 steps here. 2 very long steps, right? First step. I don't do a lot of steps, but this week, yeah, we got like a step-by-step thing in every video. The first step is going to be substitute one variable out. We're always going to be eliminating one of the variables with substitution. We'll talk about what that means in the actual problem. And then we're going to take the derivative once there's only one variable. So again, don't take the derivative when there's multiple variables. Wait for there to only be one variable. And find the max or min. That's what we're doing today. First step is going to be, we need to get a function with only one variable. And there's actually a couple more steps here, but these are like very high level, broad steps. But there's a lot of things we're going to be doing today. So stay tuned, be patient, and ask questions. All right, example number 2. We'll start with a more straightforward example, and then we'll go to a less straightforward example. Find 2 positive numbers x and y that maximize q. And specifically q here is going to be x squared times y. So we want 2 numbers that when we multiply them and square the x1, that value, that product is as big as possible. All right. And we have a requirement, a restriction. Because if we didn't have a restriction, you could just pick a bigger and bigger number, right? 1 million and 2 billion. No. Let's do 2 trillion and 5 quadrillion, right? So we do need this constraint. That, all right, maximize this product if they only add up to 2. So 2 billion is not going to be a valid option. All right, so the second thing, this is what's called our constraint equation. And the first equation, it's what's called an objective equation, or an objective function a lot of times. So in our step-by-step process, we substitute one variable out using the constraint. And we'll take the derivative using the objective function. All right. So we're going to start by trying to substitute with our constraint equation. We need to use substitution from the constraint equation to remove one variable from our objective function. So you can either solve for x or for y. I like solving for whichever one I think is going to be a little easier. It's a little easier to plug something in for y. Let's solve for y, right? If we plug in something for x, If we substitute x out, we still have to square it. So I'm going to solve for y. That's how we're going to start here. We're going to solve for y. And again, x would work as well, just would be a little bit messier. So we solve for y, we subtract x from both sides, and we're going to get y is equal to 2 minus x. If y is equal to 2 minus x, we can plug that into our objective function and eliminate one of the variables. If y is equal to 2 minus x, that means that q is going to be x squared times y. But what is y? Y is 2 minus x. Again, 2 minus x, that's the same thing as y. That's the substitution method we're talking about. And now this is really great because we're going through all the colors. We have a function of only one variable. Right, so now this is great. I really am going to use all the colors. Now we only have one variable. We have successfully completed this first objective. Now our objective function only has a single variable. Let's write that again. Q is equal to, and let's distribute as well. X squared times 2 minus x squared times x. We're going to have q is equal to 2x squared minus x cubed. Great. Function of only one variable. So we have successfully completed this step. We need to do step 2 now. Take the derivative. Once there's only one variable, so we're good to go. We can take the derivative and then find the maximum and minimum, or maximum or minimum, right? Here in this problem, we only care about the numbers that maximize q. We want to find the max. So check at the endpoints. And we will look for local extrema. So the derivative of q, we can call that q prime. Use the power rule. It's going to be 4x minus 3x squared. There are relative extrema potentially at critical points. A critical point is when the first derivative is undefined or equals 0. Well, this is a quadratic equation. We can factor to solve this, factor out an x, and we're going to be left with 4 minus 3x. We're going to have critical points when the first thing equals 0, or when 4 minus 3x equals 0, when x is equal to 4/3. So 2 critical points here. And again, we need to find what is the y value, or in this case, what is the q value here? You just plug it into our q function, right? This is our q function right here. And that's going to give us the value of q. Again, we want to maximize q. So when x is equal to 0, we get 0 minus 0. That's not very big. When x is equal to 4/3, we get some number. Oops. That's my Google calculator right there. Get 2 times 4/3 squared minus 4/3 cubed is going to give us 1. Oh, it's going to be a fraction. I guess I should probably do it by hand. What about 1.9? 1.19. All right, and technically we plug in thirds, or 4/3, right? It's 2 times 4/3 squared minus 4/3 cubed. It's going to be 2 times 16/9, be 32/9, minus 64/27. Multiply the first one by 3/3, you'll get 96/27. So 32/27 is what that y coordinate is. So far we have two candidates, and I know which one's bigger. So far this candidate is looking the most promising. But we have to check the end behavior for a global extrema. Find what the actual biggest value is. We have to look at the ends. And the ends are not super easy to find here. And it all goes back to this. We need two positive numbers. To check the endpoints, look at, okay, what has to be true about x? All right. Well, if x and y are positive, let's look at our constraint equation. Well, if x and y are positive, x has to be positive and y has to be positive. Right? If both x and y have to be positive, that means the biggest they can ever get is 2. Right? Because if x is bigger than 2, if x is 3, for example, then y would be -1. So the smallest x can be a 0, the biggest x can be is 2. We also have to check when x is equal to 2. We'll plug that into Q as well. And we'll get that Q when x is 2 is 2 times 2 squared minus 2 cubed. Simplify that out. Okay, so when x is 2, the Q value is 0. So now we have our boundaries. We have our critical points. So to find the biggest value of Q, we look at all of these Q values. So our Q values are 0, 1.19, 32/27, and 0. Well, we just choose the biggest. And then we're done. So the biggest value is 1.19. So this is where our absolute maximum will occur. 32/27. Right? So max value is 32/27, and that occurs when x is equal to 4/3. Yeah, when x is 4/3. Now let's check whether we've answered the problem. The problem says find two well, right off the bat, we haven't solved the problem, right? Find two positive numbers that maximize Q. Well, we found the x value that maximized Q, but we still need the y value. So we're going to use this constraint equation to find the y value. All right, so if x is equal to 4/3, well, actually, this form is a little easier, but you can use either form of the constraint equation. To use y is equal to 2 minus x to find the y value. The modified constraint function. Again, so y here is going to be 2 minus our x coordinate, which is 4/3. 6/3 minus 4/3 is 2/3. So the maximum value occurs when x is equal to 4/3 and y is equal to 2/3. That's the biggest way that we can maximize this Q. Wait, do I have Q? Wait. Oh, this is the wrong Q, by the way. Q is, why? This is really the wrong Q. Goodness, I don't know where that came from. Our Q is x squared times y. So it's 2 squared times y, which we said was 2 minus x. So the Q value for this last boundary was still 0, but this is the actual function. Which looks similar, but yeah, let's be correct. Yeah, that's a problem. That was one problem. That's the simplest problem. That's the simplest problem. And they only get more complicated. So again, this is a section that a lot of people struggle with, which is why this video is so long. We're going to do another example of a harder problem, and then another video with another example, okay? Again, don't hesitate to ask questions here, because unless you're a mathematical superstar, you're probably not going to be able to do all these on your own. Even if you're a actually asking questions is part of what makes someone a mathematical superstar. So feel free to pause the video right now, go get a drink, go cry a little bit in the bathroom maybe, I don't know. And then when you're ready, play the video and we'll do another example together. Example 2. All right, so example 2, we're actually going to look at, we're going to take one from the textbook. Actually, spoiler alert, that last one was from the textbook too. All right, and I'm just going to copy this down. Got a lot of words. It's going to be number 16 in the textbook. All right, and it says, it says we have a closed rectangular box with a square base and a volume of 12 cubic feet. And that's to be constructed from 2 different types of materials. The top of this box is made of a metal costing $2 per square foot. And the rest of the box is wood, which costs $1 per square foot. The question is, find the dimensions of the box for which the cost of materials is minimized. So these questions can get a little long. All right. This is example 2. All right. No, this is example 3. Oh, my word. This is the second time this has happened this week. I just have the wrong example number. All right. So this is example 3. Don't be tricked. All right. So we need a picture because remember, how do we start? We start with the constraint function, not constrain, constraint function, substitute something out so we can take the derivative of the objective function. We don't have any functions yet. Good luck. All right, so we need to draw a picture and get some variables, get some functions, modeling. What is our constraint? What is our requirement? What is our objective function? What is the thing we're trying to minimize or maximize? All right, well, let's look at this information. We have a closed rectangular box. Draw a picture. All right, watch this. I remember when I was younger, how impressed I was when I drew my first little three-dimensional box. It's not that great of a box. That's what we've got. And it has a square base. That's very important right here. Square base, which means that if we call this width x, the other part of the base also has to be x. The height doesn't have to be x. It's a square base, but it's a rectangular box. It's not a cube. So we'll call the height some y. We've got a picture. That's great. And it's to be constructed from 2 different types of materials. The top is made of a metal that costs $2 per square foot. And the rest is made of wood, costing $1 per square foot. Find the dimensions of the box for which the cost of materials is minimized. Ooh, that's good to know. Cost of materials is minimized. What are we trying to minimize or maximize? That's our objective function. Okay, so we want to minimize a cost function. We'll have to find this function. What's our constraint? This is our objective function. Well, this will be our objective function once we fill in the blank. What's our constraint? What's the requirement here? So a couple things might jump up as requirements. We have cost. Oh, wait. Cost can't be a requirement, right? Cost is cost. We've already talked about cost. Cost is our objective function, so let's ignore the cost. What's our other requirement for this box? The other requirement for this box is a volume of 12 cubic feet. So our constraint is going to be the volume, 12 cubic feet. So fill this in, and we will be good to go. That's when we can start the problem that took really a long time in the beginning of the video. So cost equals, this is going to be our objective function. And we have to fill in the blank here. This over here is our constraint equation. Let's start with the easier one, our constraint equation. The volume is 12 cubic feet. Well, what's the volume of this box? The volume of a box is the area of the base times the height. The area of the base, that's just x times x, or x squared. And the height is y. We actually have the same function as before. Part 1, we were maximizing q, which was x squared times y. Here, now it's our constraint function. So our volume is 12, and that's going to be x squared times y. This is our constraint equation. And now we have to minimize our objective function, which is our cost function, which is more complicated. All right, so we want to find the cost of this. So if we're making a box, the cost is going to just be the cost of the bottom, plus the cost of the top, plus the cost of all the sides, right? So our cost here is going to be the cost of the bottom, plus the cost of the top, plus the cost of 4 sides. And a lot of times it's a good idea to start off like this. I don't expect you to know, oh yes, the cost is 5x squared y plus 2x cubed y to the 5th power. No, right? Just break it up into little pieces. If we have to build a box, what are the costs of the materials? Well, we got 6 sides of this box. Let's add up the cost of each side, and let's figure this out individually. So, what do we know about cost? We know about cost is $2 per square foot for the top, and the rest is $1 per square foot. So the top, $2 per square. Right, this right here is $2 per square foot. The other ones are $1 per square foot. This is good to write down. $1 foot? Nope. $1 per square feet. So we just have to figure out, well, if the bottom's $1 per every square foot, how many square feet do we have in the bottom? So the base right here is x times x square feet. So the base is x squared square feet. And we have to, and the cost is going to be $1 for every single one of those. So the cost of the bottom of the box is 1x squared. Let's move on to the top. So the top, well, the area of the top is the same as the area of the bottom, right? It's just going to be x times x. So the top is going to be, again, the area of the top is x squared, but this time the top is made out of metal, which costs $2 per square feet. So we have the area of the bottom, we have the area of the top, and then we have the cost of the sides. So each side, there are 4 of them. There's going to be 4 multiplied here, times the cost per square feet. It's $1 per square feet. Times how many square feet on each side. So look at each side of this box. The side of this box is going to be x times y square feet. So let's simplify this a little bit. We got our cost function. This is great. We are almost ready to start this problem. You can see why I'm giving you guys a bonus video on this one. This is a tough section, all right? But it's not too bad. Once you do a bunch of these, they're very long, right? Once you do a bunch of these, you start to pick up on patterns, okay? And they get a little bit better. So what is our cost? Our cost function, this is our objective function, is 1x squared plus 2x squared. Well, that simplifies to 3x squared. Plus 4 times 1 times xy, that simplifies to 4xy. Great, we got our cost function. All right, so we have our constraint equation up here. We have our objective function right here. So now we have all the stuff, we can solve this just like we did example 2, which I'm sure made perfect sense. All right, but if it didn't, we'll do the same thing again here. Let's go all the way back to the beginning of today. Well, the beginning of this video. We need to substitute one variable using the constraint equation. And then we'll plug that into the second equation, our objective function, and eliminate one of the variables, and then we'll take the derivative. So it's your choice. Our constraint equation's up here. Your choice. Do you want to solve for x? Do you want to solve for y? Again, I think it's easier to solve for y. We don't have to worry about a square root or anything. So let's use this constraint equation and solve for y. We get 12 equal to x squared y. This is our constraint equation. And we're going to solve for y. Again, solving for x works. It's just a little harder. So divide both sides by x squared. We get y is equal to 12 divided by x squared. Excellent. Excellent. All right. Oh man, it's been a long day for me. Probably been a long day for you guys too if you're watching this video. Anyway, don't worry. There's light at the end of the tunnel. So we substitute this into our constraint, our objective function, right? Our cost, C, we said was 3x squared plus 4xy. What we are going to do is we're going to plug this in. This is equal to y. So plug it in for y. That's going to give us a function of only one variable. Our function is 3x squared plus 4x times y, which is 12 over x squared. And this is great news. We are back to the previous section almost. We have a cost function. We have a function that we're trying to minimize. We can minimize this by looking at extrema, finding global extrema here. Find the global extrema, we need to find critical points. We need to look at the ends of this function. We'll just choose whichever one's the smallest, whichever one has the smallest cost. And this one, you're going to kind of notice a pattern with a lot of these, right? We have a box. These are dimensions. So the ends of our domain, right? These need to be positive dimensions. So just like last time, right? The ends of our domain are actually kind of silly situations. The ends of our domain is when the base of the box has width 0. Well, we're not going to do that, right? It's a limit. It's not going to be really anything. The other end of the domain is when the height is 0, which again is a very absurd situation. So here, really, to find the minimum, we just need to find the local minimum here for that logic. And I don't need you to write that logic to me every time, but maybe just understand it, that technically we have to check the endpoints of our domain here. But the ends of our domain in a lot of physical situations, not all physical situations. So kind of ask yourself on each problem, are the endpoints of our domain here a silly situation? And then you can save yourself a little bit of time here. I'm okay with you skipping that. Just be very careful to make sure that you can skip it. So we need to minimize this function. We could take the derivative right now, or we could simplify first. Simplifying first is usually a good idea when you can. We have 4 times x. Remember, this is like 4x divided by 1. So multiply those numerators together. We get 48x. And the denominator is x squared. Let's just cancel one of these x's, right? This x cancels with that x. So our numerator becomes 48. And our denominator becomes x. Ooh, we get to take the derivative of a reciprocal function. So remember over here that 48x, that's the same as 48 times 1 over x, which is the same as 48 times x to the negative first power. Right? Negative exponents mean reciprocal. And writing it in this form is going to be a lot easier to take the derivative. So derivative, let's use the power rule. We'll get 6x, and then we need to take the derivative of this guy over here. Exponent comes down, makes it a minus 48. Subtract 1 from this exponent will be x to the negative second. And we need to find when this equation is equal to 0 or when it's undefined. That'll be our critical points. Let's copy this down again. C prime is equal to 6x minus 48 x to the negative second. Remember a critical point when this derivative equals 0 or is undefined. So it's undefined when x is 0, right? Because again, this right here is 48 divided by x squared. So it's undefined when x is 0. We already said why x equals 0 is a silly situation. It's not in our domain. I can't make a box with width 0 feet. All right. So we're just going to look at the other case. When 0 is equal to 6x minus 48 over x squared. We need to solve this equation. This is a rational equation, not a quadratic equation anymore, a rational equation. Got to remember back to your intermediate algebra. To solve a rational equation, you multiply both sides by the LCD. Which in this case, we only have one denominator, so our LCD is not too bad to find. Our LCD here is x squared. We're going to multiply the left-hand side by x squared. And we're going to multiply the right-hand side by x squared. We'll have to distribute. Left-hand side, 0 times x squared. That's just 0. I like that multiplication. First part of the right-hand side is 6x times x squared. That's 6x cubed. The other one, x squared divided by x squared cancels out. We're just left with that 48. And now we only have an x cubed, so I can isolate the x cubed and then cubed root both sides. So let's add 48 to both sides. 6x cubed equals positive 48. Divide both sides by 6. We'll get x cubed is equal to 8. Take the cubed root of both sides. And remember, if you ever take the square root, you do need a plus or minus. We're going to take the cubed root of both sides. Cubed root of 8 is 2. Ah, great. We're done, right? What were we trying to do? How many pages ago is this example problem? Find the dimensions of the box for which the cost of the materials is minimized. The dimensions of the box are x equals 2. Well, that's not helpful. There are 2 dimensions of the box, right? We need to find out what y is too. So our x, we got that. The base of the box will be 2 feet by 2 feet. But just like last time, to find the y value, we'll use our constraint equation where we plugged in. Y is 12 over x squared. So let's use that. All right, so we know, again, we need to find y. We said y was 12 over x squared. So if x is 2, we get 12 over 2 squared. 12 over 4 is 3 feet. So we are basically done. We have a box, just like before, which is now green, apparently. Maybe not just like before. And the base is x, which we said was 2 feet. The width, well, it's a square base. So this width is also 2 feet. And the height is y, which we said was 3 feet. And this is our final answer right here. You could also say the box is 2 feet by 2 feet by 3 feet, right? If you wanted to say that. That's okay as well. Either one works for an answer. Just what everyone wants, a 35-minute calculus video. Anyway, I will have another extra video with an extra problem if you want to see another problem like this. Maybe a little different. We'll have to find the objective function, find the constraint function, solve the problem. And yeah, this is our cost minimizing box. Good luck.